Alright, hello everyone. We're going to do the Kirchoffs rules practice worksheet here. And this is brand new setup here, so you all got to be very understanding here while I get some kinks worked out. I'm going to pull up, did this in February, but we're going to go over it here. Complete the worksheet. Okay, so if you need a copy of the worksheet, here it is. There's some, these are the rules, Kirchoff's current and voltage laws, right? They're the junction rule and the loop rule. We're going to use these to analyze these circuits. And in order to analyze a circuit, you need to know each current through each leg of the circuit and the voltage drop across each resistor. That's usually what if you've done all of that, you have analyzed that circuit. And so there's some examples here at the beginning, which we found this online, right? Okay, here's number one. Let's switch over to our document camera, which I don't have working yet for streams. I don't know how to stream this yet, but I will be able to. At the very least, we can do these recordings here with them. So, all right. So let's analyze this circuit. Okay. Let's start off with a junction rule. Okay. I know I have this junction here. Actually, let me grab this. Okay. Let's do a junction rule for this junction right here. Okay, because we have I1 and I2 coming in. There is a third current. It's not labeled. We have the value of that current though. That's I3. Let's just put it, and remember, as always, these arrows, these are potential, right? These are our guesses of the potential direction of current. We can go through this whole Kirchoff's process, find out, we got it backwards. It's just a negative sign, right? If we get a negative for any of these currents, we know that we have to flip the direction. Right? So let's do a junction rule. So we're on number one. Here, make sure I'm, all right. I have the two currents that are going in, I1 plus I2, equal the current that leaves, I3, which we happen to know is 3 amps. Right? That's Kirchoff's junction rule. The currents moving into a junction equal all the currents leaving a junction. All right. So we have two unknowns here. Okay. So we need at least one more equation, and we'll be able to solve those. Okay. Let's do a loop. Now let's do one of loops. I'm going to start my loop right here. I like starting right behind a battery here, because as I cross the battery that way, that'll kick us up 9 volts. I'm going with assumed direction of current, so that would be a voltage drop. That would be a voltage drop. That's going to be my first loop right there. So let's go ahead and do that loop. All right. All right, so I start off at 0, okay? All right, I'm going to go up by 9 volts. I'm going to go down by 3 ohms times the value of I1. That's the IR drop. I'm going to go down by 2 ohms times the value of I3, and that brings me back there, okay? So I actually have a value for I3 there, so let's rearrange this. All right. Okay. We can actually solve for I1 here. Right. And since we have this, let's go ahead and, right, so there's I1, right, I have this relationship here, let's go ahead and plug that into there. Okay. So the only thing left in the circuit, now let's do one more loop here to get this variable involved here so we could figure out that voltage drop there. Let's do a loop. We'll start right here behind that battery. Okay, so I'm going to rearrange my papers a little bit. Okay. So 0 equals, I'm going to go up by epsilon volts. All right, I'm moving with the direction of assumed current, so this is a voltage drop. Minus 4.5 ohms times I2. Okay, here I'm again traveling with the assumed current, so this is minus 2 ohms times I3. And then I'm back to start there. So then let's rearrange this. I have a value for I2. It's 2 amps, right? I have a value for I3. What's that, 15? So far, so good. Let's move on to number 2. They'll ramp up. Question 2. Okay, I'm going to be using these currents here. Okay. Let's say I1's going up here. Okay. Let's say I2's moving down there, and I3's moving down there. You know, why, looking at this battery, why assume this current's moving that way? Well, that's a big 12-volt battery. You know, maybe current's flowing in both of these directions, right? Maybe this battery's being charged here. Okay, and again, it doesn't matter if we assumed, if it turned out current was flowing this way, we'll just get a negative value for I3. And so these are going to be, I'm about to start my loops here. This is going to be the currents I'm using. All right, so I'm going to start with a junction rule here. All right, into this junction's flowing I1. Out of this junction's flowing I2 and I3. Kirchoffs junction rule says the currents into a junction equal the currents leaving the junction. Conservation of charge. Alright, so we got one equation. There are 3 unknowns, so we need at least 2 more here. Okay, let's do, I think I went with this. Let's park behind this 12-volt battery here, and I'm going to start off with this loop right here. So I'm going to go up by 12 volts. Here I'm going with the assumed flow of current here, I2, so that's a voltage drop. Again, I'm going with the assumed flow of current there, that's a voltage drop, except that's I1. Alright, well, let's see, what other loop did I do? Let's do this loop. Okay. Let's do this loop. Okay. I like to go behind this battery here. Like, I don't care if I'm going against current there, right? Look at the way this battery's poles are labeled. This side of the battery is 5 volts higher than that side of the battery. So when I go to do this loop, I'm still going up by 5 volts there. This wire is 5 volts higher than that wire, right? At least according to this battery. Now I go here, I'm traveling with assumed direction of current, so that's a voltage drop. Here I'm going against I3, right? So this is at a lower voltage than that. By how much? By this resistor, remember Ohm's law, right? A resistance times a current is a voltage, right? So current goes that way, that voltage will drop. I'm moving in the opposite direction. Okay. So now kind of do some math here, start solving our system of equations. We have 3 equations. We could have did a 4th to get that whole loop there, but it shouldn't be necessary. Let's go ahead and start trying to isolate and eliminate variables. Okay, so I know that I1 here is I1 is I2 plus I3. So let's substitute that in for that. All right. Okay. Let's distribute so that's minus 3I2 minus 3I3. Okay, I can combine like terms. Negative 4 minus 3 is negative 7. Okay, so now I have two expressions that contain both I2 and I3. Alright, so let's maybe add that over. I'll get 3. Actually, yeah, I got 3I3. Let's see how did I do this before? Oh, you know what I did is I added these. Yeah. Let's do that. Let's take this equation and this equation and let's add them. Okay? I can add up the left side. 0 plus 0 is 0. Alright, I add, now we're combining like terms. There's my voltage and my voltage. Let's add those. Okay. I1 terms, there are none. I2 terms, I have negative 4 plus negative 7. Okay, negative 4 plus negative 7. Alright, that's going to be, make sure I think this is when we did this in class. I think I made a arithmetic mistake here. Negative 11, I2, and then I3 terms, right? 2 plus negative 3 is negative 1. Huh? Good, good, good. And let's clean this up a little bit. Alright. Now, so it's still got I2 and I3. We can get I3 all by itself. Okay. Now wherever I see I3, I can substitute that back into. Alright, so maybe we take it back up top here. Add that over, subtract that over. Alright, and now have an expression for I3. I have an equation here that's only got one unknown, I2. Let's solve for it. What's 2 times 17? What's it, 39? I hate arithmetic, you guys. I hate arithmetic. 15 times 2 is 30. So 34. It's probably 34, right? Yeah, it's 34. Negative 2 times negative 11I2, that's going to be plus 22I2. Alright? So let's add 34 over to there. So that's going to be 39 volts equals positive 4 plus 22, so it's going to be 26I2. I get 39 over 26 equals I2, which is 1.5 amps. First of all, it's positive, so the direction we assumed for I2 is correct. Alright, and now we can go back and start, now that we got a number for I2, like right here, I see here's an expression with only I2 and I3 in it. Let's plug this value for I2, and now this will only be, right, 17 equals 11 times our value for I2 plus I3. All right. So I got 17 equals, this turns out to be 16.5 plus I3. And subtract over, I get 0.5 amps equals I3. Alright, I got I2, I got I3. We can go back to our original junction rule. I1 is the sum of those. Which, I mean, if I2 is the sum of, if I1 is the sum of I2 and I3, alright, it's going to be 2 amps. There were no unknown voltages here. The 3 unknowns were the 3 currents. Okay, question 2 is done. Okay. Let's do question 3 here. Right. There's the question. Make sure. Alright, so the unknowns here, we have all 3 voltages, we have all the resistances, so I2, I2, and I3. Right? That's our unknowns. So let's set up some, how do we want to do this? Let's say I1 is going that way, and 18 volts is bigger than 12 or 6, so let's just say both of these are being charged. We could be wrong. We might get a negative value for one of these currents, including I1 even. Okay, that just means that the arrow was wrong. It isn't the end of the world. Okay, so let's start with a junction rule. Okay, all 3 currents come to meet at this junction, which, you know, that doesn't have to be a criteria. As long as we have one equation for each unknown, we will be okay. But why not do there? So I see I1 coming in, I2 and I3 leave. So I1 equals I2 plus I3. Bam, we have one equation already that relates these 3. And now let's do a loop. Let's park right behind that 18 volt battery. So the first thing that we do in our loop is we kick up by 18 volts. Alright, I'm moving with I1 here, so this resistor represents a voltage drop. Okay. Now remember, we don't care. We happen to be going with I2 here, but we don't care. For a battery, this wire is 12 volts higher than this wire. So when I go that way, I'm dropping by 12 volts. And then I'm back to start. Okay. So this one, we can make quick work of this. 18 minus 12 is 6. Right? Move that over. I1, we're going to get 3 amps. Off to a good, strong start. Okay. Let's do another loop. Let's park right behind this battery. Okay. Again, I don't care. I'm going against current here. It doesn't matter, right? For batteries, right, this wire is 12 volts less than that wire. Right, so when I go that way, I am going to a higher potential. So I'm going to go up by 12 volts in our loop's logic here. Hey, this resistor, we're traveling with I3, so that's a drop. Minus 6 ohms, I3. Okay, now I'm going to, it doesn't matter that I'm going with the current here. That's resistor logic. Now I'm talking about a battery. This wire ought to be 6 volts higher than this one because I'm going across that way. So I'm going to a lower place. Let's subtract that off. Okay? And then I'm back to where I started. So now I get 0 equals, so we're going to do that subtraction, 6 volts minus 6I3. 6I3 equals 6. I3 equals 1 amp. Alright, I've got 2 of the 3 unknown amperages. Just plug it in. Get I2. Alright. There we go. Bada bing, bada boom. Okay, so here the currents do have arrows already. In fact, we're even given one. Okay, the click back over here. Right, this battery here, unknown voltage. Okay. Let's do our first loop. We can do a junction rule right here. Okay, I3 is the current coming in. I1 and I2 are leaving. Alright, junction rule, currents flowing into a junction equal to currents flowing out. Okay, let's park right behind this known voltage here, and we're going to do this loop first. Okay, so let's see, we get 0 equal, we're going to kick up by 18 volts. Alright, I'm going to minus 4 ohm, I'm moving with I3 here, which is 2 amps. So this resistor then, if I'm moving with the current, that resistor is a voltage drop. Right? V equals IR to find that voltage drop. So this is an IR drop for that resistor. 4 ohms times 2 amps. 4 times 2 is 8 volts. So we're going to subtract 8 volts there. Okay? I'm moving with I1 now. Right? So that's also a drop. Minus 7 I1, and then I'm back to start. So here, right, we have one equation with I1's the only unknown. We can already rearrange for I1 here. Okay? So let's add that over. So I get 7 I1. 18 minus 8 is 10. So I1 equals 10/7 of an amp. Okay, I2 is already known, right? That's that, or sorry, I keep doing that. I3 is already known, it is 2 amps. So let's go ahead and we can already solve this. So I3 minus our known I1 equals the unknown I2. I3 is 2 amps minus my 10/7 of an amp equals I2. 14/7 minus 10/7 is 4/7 of an amp is I2. Okay. So for this last one, now we need this unknown voltage. So let's do another loop here. Let's get that V2, that unknown voltage V2 in there. Let me go back and see how much of this is still on screen. Alright, let's do another loop that gets this in the mix. Let's park right behind that. So our first, we're going to kick up by V2. Right, and we'll do this loop here. We know that this is a drop of 4 ohms times 2 amps, so this is a drop of 8 volts. Okay, and then this resistor will get in, that'll get I2 into the mix, which we know, and then we should have everything to solve there. So 0 volts. All right, we're going to kick up by V2. Let's see if I could get this. All right, I'm going to kick up by V2. We're going to drop by 4 ohms times 2 amps, so minus 8 volts. Okay. And then the last part, the last term here is I2 times 3 ohms, so minus 3 I2. We have a value for I2. It's 4/7 of an amp. Okay. V2 is the only unknown here. Let's rearrange for it. Okay. And solve. So what's that? Minus 12/7. Okay. Alright, we won't do equals. We'll say And oh gosh, what's 8 times 7? So it's what, 49 plus 7, so it's that 56. Am I doing that right? 56 sevenths minus 12 sevenths equals 44 sevenths? Oh, and sorry, this is not in amps. It's in volts. Let's see if we're right here. Let's check my math here. Should have got 9.7 volts. What did I do wrong here? 8 times 7 is 56. Minus 12 is 44. What am I doing? Do you guys see it? Oh. I went from plus here to minus there. So that's 68 sevenths. I wonder if that works. Okay, there we go. Alright, so yeah, 9.7 volts. Alright, we got all currents now. We got our voltage. Number 4 is analyzed. Alright, question 5 here. Alright, all 3 currents have arrows. We're going to just stick with these assumed directions here. One might think, hey, look at that 28 volt battery. Why would I1 be moving against that there? Okay, remember, when we have assumed currents, it's just to help keep our loop and junction rules consistent. We find at the end that we have a negative value for one of these. Easy peasy. We just know that that arrow was flipped before we got started. Okay, so we're just going to run with the arrows that are given here. Okay, the voltages are known, the resistances are known, so to analyze this circuit we need numerical values for I1, I2, and I3. Well, let's go ahead and get started here. Let's do the junction rule. Okay, I see I2 is going in, I1 and I3 are leaving. The current heading into the junction equals the currents heading out of the junction, a statement of conservation of charge. All right, let's do a loop rule, which is a statement of conservation of energy, as voltage is potential energy, electrical potential energy per unit charge. So the voltage increases must equal the voltage decreases. That's conservation of energy. 28 volts, 0 equals, our changes will be 0. 28 volts up. I'm moving again. I'm doing this loop right here, by the way. I'm going against what we've called I1. Okay, so that means this wire is higher in voltage than that wire by amount that Ohm's law says V equals IR. Okay, so 4 ohms times I1 is the voltage drop. If I'm moving with the current, we're going the other way, so we're going to represent that as an increase, plus 4 I1. Again, I'm moving against the current here, right? So this bottom part of the wire is at a higher voltage. If I2 is truly moving that way, it expends some voltage, expends some energy pushing through R2 that way. So when I travel this way in my loop, I'm going to a higher voltage place. It is 2 ohms times I2. That's the voltage, how much higher in voltage that bottom lead of that wire is. All right? We'll need a third equation here. Let's just do this loop here. I'll get from behind this 7 volts, the total change, 7 volts up. I don't care if I'm going against I3 here, right? That's I3. I don't care that I'm going to look at the labels. This negative sign and that positive sign says this wire is 7 volts higher than that wire. So when I go from there to there, I'm going up by 7 volts. I'm going against the current here. For resistors, I do care about a current direction. So when I go to this other side here, I'm going to a place that is 1 ohm times I3 higher. and then again going against the current flow there, so that's plus 2 I2. Alright, now we're solving our system of equations here. So let's see, if I subtract this equation from that equation, right, I'll get my I2s to cancel, and that's kind of the name of the game here, right? Eliminate variables. 0 minus 0 is 0. There's only one voltage term here. Remember, I combine like terms. There's only one voltage term there and one voltage term there. So 28 minus 7 is 21. I take my I1 term minus my I1 term, which there is none. So 4I1 minus 0I1 is still 4I1. 2I2 minus 2I2 is 0I2. And then 0I3 minus 1I3 is negative 1I3. Okay? So I can quickly get an expression for I3 in terms of one other variable, I1. That's pretty good. Okay, later in the sheet these are getting more complicated, so there's multiple steps. But what I've done already is I have an expression for I3 in terms of only one other variable. That's good, right? We're dividing and conquering here. So let's take a look here. What can I do next now? Well, because I have an expression for I1, right? I know I1 is actually I2 minus I3, right? So we got that to work with as well. Right? Let's see, what else do we have to work with here? Okay. And actually, consequently, I3 is also I2 minus I1. I got that also. Okay. And actually, let's run with that. Let's run with that. Here I have I3 equals some stuff. Here I have I3 equals some stuff. That means that stuff is equal. I2 minus I1 equals 21 plus 4I1. Okay. I can add that over, so I got I2 equals 21 plus 5I1. Alright, so now I have two expressions, right? I have I3 in terms of I1. Oh, sorry guys. Right, so I just set this stuff equal. So I know that equaled I3 according to that, and that equaled I3 according to that. So I set them equally to each other and I solved for I2. I have I2 in terms of I1 and I1 only. Alright, so what can we do now? If I go back to here, here's an equation that has only I2 and I1 in it. I now have an expression for I2 that will swap out that I2 and replace it with an I1. Okay, so maybe I plug this in for that. And 0 equals 28 plus 4I1 plus 2 times I2. But instead of that, let's plug in this. Here I have one equation that the only unknown is I1. Let's do some algebra and see if it helps us. So what's that? 42 plus 10I1. Alright. So 28, here's the voltage only terms, right? 28 plus 42 is what? 50, 70. And then positive 4 plus positive 10 is 14. Okay, so here I have a numerical. You guys can't see that, can you? Does that get better? What can? You'll have to trust me. Punch it up in your calculator if you don't believe me. 70 divided by 14 is 5. Huh? And it's negative. Right? It's negative because that arrow was in the wrong direction. Now we're still going to run with negative 5 amps for the rest of this question here. Okay? But now we know that in actuality it's the other way around. If we flip it now, if we start plugging in 5 amps for I1, we need a new junction rule, and all of our loop rules are backwards. So we're going to run with negative 5 for this. Okay, we have the magnitude of the current. Okay, we just know that in actuality it is as we thought, flowing out of that 28 volt battery and into the rest of the circuit here. All right. So now that I have a number, right, here's an expression. We can plug it in and get I2 real quick. I2 equals 21 plus 5 times I1, which we said was negative 5 amps. So that's negative 25, so that's what, negative 4 amps. We like it? So I2 is also I2 is also backwards, which we said made sense. But, we just wanted to use their assumed currents, which is fine. I think that was probably the point of this exercise here. Okay? So we have numerical values for I1 and I2. All right, we know what I3 is in terms of those. I3 is I2 minus I1, so I'm going to minus a negative, all right, which is like plus. I get positive 1 amp. Oh, keep going off screen on you guys. Don't let me get away with that, right? So I just took that expression for I3. Sorry, now that you can't see, I'll redo it. Right? It was I2 minus I1. So the I3 arrow was right. Let's go back to the problem. Right? The I3 arrow was right, so that 7 volt battery really is being charged. But I1 and I2 arrows are flipped. Right? So current's flowing out of the 28 volt battery and into either other leg of the circuit there. Alrighty, and that's question 5. In question 6, right, again we have 2 voltage sources with known voltage. All 3 resistors are known resistance. So we're looking for currents I1, I2, and I3. We have assumed directions. We will find out if they are right or not. Taking a look at this, if they are as they say they are, both batteries are outputting current, and then it adds up and in that middle leg there. So let's go ahead and take a look, see what we get. Move down. All right. So let's do a junction rule, right? Conservation of charges apply. Let's do a junction at A. I3 and I2. Let's extend these arrows. Right? I3 is moving that way. I2, this is all I2. Right? And this is all I1. Currents don't change until you hit a split in the wire, and the charges have options. Okay, so when I do my junction rule for A, I3 is leaving the junction, all right, and it should, I3 and I2 are leaving the junction. I1 is entering the junction. I flipped that, but commutative property, it's all good, right? I1 equals I2 plus I3. And that's right. We could look at B, but we're actually going to get the same thing, right? I3 and I2 are coming in, I1's leaving. So I3 plus I2 equal I1. It's another equation, it's just not introducing any new variables. It's kind of a trivial, we already know that information. So pick one junction rule here, and we'll run with it. All right, let's do some loops here. Let's do a loop that gets behind the 12 volt battery here. We'll start from right there for our loops. Conservation of energy says the voltage, right, that the electrical potential energy per charge, those increases should equal the decreases. The voltage increases should equal the voltage decreases. And by the time I get back to the same spot, those increases and decreases will cancel out. So I'm going to kick up by 12 volts as I move through this. All right, let's do the top here. I'm moving with I3. All right, which means when I go from here to here, I've consumed voltage, right? I've used up energy pushing charges through this. So I'm going to a lower place. So I'm going to subtract 2 ohms times I3. I'm moving with I1 now, so this resistor is also a drop, minus 4 I1, and I'm back to where I started from. So there, that one's all done. Okay, let's do maybe from the same spot, or actually let's do this from point A, junction A here. We'll do the bottom ones now. We'll do the bottom part. So we start off at 0 volts. I'm going to kick up by 8 volts. All right, I'm moving with I2. So that's going to be 6 ohms times I2. Oh, yeah. Right? And now if I'm doing this path here, I'm going against I3. So I'm going to a higher voltage place. How much? 2 ohms times I3. That's the voltage drop if I were following the current, but I'm going opposite the current. And there we go. Okay. All right. So we should have enough here. I1, I2, and I3 are our 3 unknowns. We have 3 equations. This should be plenty to get started with here. All right, something comes to mind here. I notice I see negative 2i3 and positive 2i3. So if I add these, I'll eliminate something. Let's do 0 plus 0 is 0. 12 plus 8 is 20. The I1 terms, the I2 terms, 0 plus negative 6 is negative 6. Oh, except that was I2. And the I3 terms, negative 2 plus positive 2 cancels, right? So here we have yet another equation, which actually, if you look carefully, ought to be that fourth one if we did all these, right? Pick up 8 volts, drop 6 I2, drop 4 I1, pick up 12. So actually what we've actually just derived there is that outermost loop. Okay, so we have more equations than we need now, but that's cool. We'll run with it. When you're solving these systems of equations, it's the more puzzle pieces you have, I think, the better here. So let's do this. Let's solve. Actually, if we combine, you know what we could do? Alright, so let's get I1 in terms of I2 here. So I'm going to add that over. Let's get 4 I1 equals 20 minus 6 I2. Alright, and I can divide it through. So let's get I1 equals 5 volts minus, 6 over 4 is 3 over 2 I2. Alright, now wherever I see I1, I can go ahead and plug that back in. Alright, here is an expression that only has I1 and I2. Oh wait, that's just where this came from, so let's not do that. Okay, maybe we'll put this, let's get this in terms of I3 maybe. Alright, so let's see. 2I3 equals 6I2 minus 8. So that means I3 equals 3I2 minus 4. Alright, I1 equals something involving I2, I3 equals something involving I2. Maybe we take these and plug it back into our original junction rule here. Alright, so let's put it in terms of I2, because that's what we'll be solving. For I2 equals I1 minus I3. And now we'll plug in our expressions for each. I'm going to rearrange paper here. So I2 equals 5 minus 3 halves I2 minus I3, which is 3I2 minus 4. Alright, so right now, before I go any further, I'm going to distribute that negative, because I know I'll make a mistake if I leave it hanging too much. So I got 5 volts minus 3 halves I2. Okay, but now I'm going to distribute this negative, so I'm going to say plus 3 I2 plus 4. Alright, because... oh wait, see, I did it already. I'm going to minus 3 I2. But I'm going to subtract a negative 4. I'm going to add 4. Alright. So I have only I2s now. Okay. Let's do some algebra. Okay, first of all, 5 plus 4 is 9. Minus 3I2 plus 9. Alright, I'm going to add 3I2 over. So here I have 4I2 equals negative 3 over 2. Okay, then I'm going to add 3 halves. Right, so 4 plus 1 1/2. Right, because that's the decimal version. Oh, let me make sure I'm on the page here. Right, I added that over, combined my like voltages, plus 3I2. 1 plus 3 is 4. Right, so here I have minus 1 1/2. I'm going to add that over. So I'll go to 5. Well, I'm going to jump to decimals here. I hope you don't mind. You should know. You should see that 3 halves is 1.5, right? So I'm going to add 1.5 I2. All right, 9 over 5.5. (1.6 amps). For I2. Okay. Good, good. Now let's find a expression that has I2 in it, because it's got a numerical value now, and that'll help us knock out another one of these. So then we said I1 was 5 minus 3 halves I2. So I1 equals 5 minus 3 halves. Bad glare. Three halves I2. 2.4. Okay. I1 equals 2.6. Alright, and then I3, right, it's I1 minus I2. Per our original junction rule. So there you go, Kirchoff's loops. Okay, the kind of breakdown of the rules at the beginning is helpful. Okay, but if you're not super strong with solving systems of equations, which, I mean, as you remember from class, and you may even gathered from watching this video, it's kind of an art form, right? Write out the equations that you have. Look at what variables you can isolate. Oftentimes you got to go through many steps to get there. You can't always just take solve for one, bam, plug it back in. Sometimes you got to take two expressions and solve them for something that can get plugged into one another. Let's just, if we quickly even solving systems of equations. We can even look for videos, right? These are all videos on solving systems of equations. So if you're good at doing the loops and good at writing out the expressions, but you can't take it to that next step, I mean, this is what you need to remediate yourself on. Okay, here's one. I'm not sure who does this, but I'm sure Khan Academy has it, right? We could even add that to, right, systems of equations by elimination, systems of equations with substitution. There you go. Okay, so this is the part there. If you're struggling, how did he do that? Why did he do what he did there? It's because I'm just doing work until I get a variable by itself with a numerical answer. And you may remember from class, we had to take a couple swings at this. I had a simple, it was minus 3i on one line, and then it became plus 3i on accident, and I had something totally different. Okay, I even had to refilm some of the questions just now because I goofed up or I stalled out and was like, what do I do next? And I had to take another swing at it. So it's an art form, right? It's part math, part art. Just stick with it there. Here, let me, did you guys see? Right, I was talking at the camera while I did this, right? Solving systems of equations, I'm just on videos here, right? Here are all videos on solving. If you miss Sal from Khan Academy and his staff there, bam. Okay, these are all things that will help you do these types of problems. Follow Kirchoffs loops to set up the system there. You need one equation for each unknown. Then go through and do algebra until you're there. All right, practice. Hopefully this worksheet was good practice, but you can keep doing it. Again, remember, this is at a Unit 9 for AP Physics 1. So this year, right, with the school closures and such, you don't need this for the AP exam. You don't need this for the New York State Regents. You will need this if you continue your physics education on AP Physics 2, for example. It'll come up again. And then in undergraduate physics. So thank you for joining me. Shoot me any questions. Let me know if I goofed anything up. I know this last one, number 6, I got different answers than we had even had in class. So maybe you can find what was different between this time and that time. And thank you for watching, and I'll talk to you soon.